Good evening, everyone. As Gary mentioned, and also Linda followed up, the mathematical modeling is the backbone of our CSO control program. Why do we do mathematical modeling? We could actually construct a project like a retention basin, follow up with post-construction monitoring to understand the improvement in water quality that we get out of this project. But it's a trial and error process. You need to be able to construct a lot of it and then monitor each one of them. Instead, mathematical modeling allows us to upfront evaluate the potential benefits that we can get from combinations of CSO control measures. So this gives you more of an informed decision-making framework where you can look at the different options and see which one gives the maximum benefit for in terms of the water quality, and then choose the projects and then put them into the capital improvement planning process. These efforts have been done over a large number of years. 20, 25 years of work went into the water quality models that we are going to review today, and also the watershed models. So just a brief introduction on the modeling process. I just gave a little bit of an overview of what happens in the watershed. So there is a rainfall that occurs on the land surface, gets into the sewer system, along with what happens in what comes in during the dry weather period, the domestic wastewater, and then it gets into the combined sewer system, which is controlled by a regulator structure that traps it and then sends it to the treatment plant. And when the capacity of this regulator is exceeded, then it goes out as an overflow into the waterways. So in essence, what these models are, a mathematical representation of the physical, chemical, biological processes that happen both in the land surface areas and how they get transferred through the sewer system and then eventually into the waterways, and how they are impacting the quality of waterways to support the beneficial uses we are talking about. So it's an EPA endorsed methodology for the long-term control planning studies. And what we start with is this construction and calibration of the model to make it as realistically as possible to represent the system. So you need to do monitoring of your system, both in the within the sewer system as well as the waterway, to understand what the conditions look like for the specific rain events that you observed for, and then use that as the information to set up the mathematical equations. And then once you construct the model, the next step is you can use them now in a planning mode to look at what will happen within the system for a range of climatic conditions or operational conditions. Could be like, what happens when there's a large storm that is, projected to be in the next couple of days. You can use that in a forecast mode to understand what happens, what can happen. But in this context of long-term control plan, we are really using them for evaluation of a range of CSO control measures to help with decision making. So in big picture view, these models, we call them integrated models because they are components based. The first part is this, what you see on the 1/3 of your left side of the screen is the watershed model that looks into the land uses, the parks and residential land uses and so on. And they look into how the runoff gets generated after accounting for all the losses that happen to the rainfall and how that gets translated into the runoff. And then the second step is, we feed them, that results in the combined sewer overflows or storm discharges from the watershed model. Then we put them as the inputs to the water quality model. This is one of the waterways, Coney Island Creek, where you can see the drainage area around. Oops, I'm sorry. Press the wrong button. So once we provide the information on overflows, then there is a kinetics that happens within the water body. how this water body interacts with the larger estuarine system, how the water flows, accounting for the vertical mixing, and then the tidal effects and so on, wind effects, the temperature, air temperature exchanges. And then adding on top is the water quality component, which really looks at the chemical and biological components of various pollutants. And this is done like a building block system. So the simplest one from a modeling standpoint is the pathogens. And then the next complexity comes from the dissolved oxygen modeling, and then comes the toxics modeling. So you will see in that back, there's a flow chart associated with each one of these. You will see lots and lots of components as you go down from pathogens to the toxics modeling effort. So in terms of the modeling framework within New York City, we had been using a range of tools, for 10, 15 years. But then back in about 10 years ago, we selected a common framework of InfoWorks for the entire city, which actually has several advantages to it. It's a faster model in comparison to some of the other ones that we had used. It had good GIS interface, geographic information system exchanges, and then also it was very easy to use. So what you see on the right side of your screen is the drainage area. The one in the middle yellow color is the separate sewer system. This is for one of the wastewater treatment plant drainage service areas. And then what you see here are the combined sewer system on either side. And then very close to the waterway, what we call as the direct drainage, which runs as overland flow directly into the waterway. So what you see here also are the sewers. New York City has over 7,000 miles of sewer system. So not every sewer is built into the model. Generally 48 inches and larger pipes are included. So what you see here is that network taking the flow from upper portions of the system towards the treatment plant. And all the control elements like the combined sewer system, interceptor sewers, the regulators, outfalls with tidal boundary conditions, these are all included in the model to account for the dynamic conditions that happen within the sewer system. And this is more of a schematic of the watershed model. So the first component is the runoff model that translates the rainfall into runoff, accounting for all the initial losses that happen in the system. And then it feeds those runoff into the hydraulic model, along with the dry weather flow, that is the sanitary flow that is coming into the sewer system also, and it accounts for all these tidal influences, regulators, outfalls, etc. And then what it produces are these flow and also the pollutant loading that is coming from each of the outfalls. So we have set up, this is another advantage of the InfoWorks models, where it's able to track the sanitary and storm fractions of flows within a combined sewer system, because it's a mixture of these two that get into the waterways. The status of the models, this is as of a couple of years ago, where we constructed and updated them using the physical data for, that we have collected during different projects over the last 10 plus years. And these have been calibrated based on the plant inflows. We have hourly plant flows coming into each of the treatment plants. They are tracked. And then we also have temporary monitoring that has been done in every one of our drainage areas to support various projects. These are at a planning levels very suitable for doing the CSO control planning. So you're able to look at whether it is green infrastructure projects, or is it a retention facility, or flow reduction strategies using our water conservation program. We are able to evaluate a range of those and then see how they benefit the overall water quality. And what these models have been used to set up the what we call as the watershed water body facility plans for each of the waterways. These have been approved by the DEC, and we are using them as the foundation to develop the next step of long-term control plans. And these models have been used also for the green infrastructure evaluations that you are familiar with from our 2010 Green Infrastructure Plan. So these models have been extensively peer-reviewed by academics and also practitioners. And they have developed, or they provided several recommendations for improvement. And some of these are listed here, like improving the imperviousness using satellite imagery. What we used to previously use is the information on the roadways and building footprints that were readily available. No information was available on driveways or sidewalks and so on, so we arbitrarily used a 10% adjustment factor, and here, with the remote sensing data, we overcame that assumption. And then improved calibration based on hydrology, meaning they recommended putting meters, flow meters, well upstream in the watershed, so you're able to capture the hydrology behavior. Most of our previous metering was near the regulators or well downstream, in the downstream areas. Adapting some standardized methodology for assessing the adequacy of calibration. How good is a model? How well does it represent the real world conditions? And then to also conduct some sensitivity analyses on using both spatially varied data like a radar rainfall data, and then you also use the NOAA gauges, the gauges maintained by the federal government in the metropolitan area. So you will see some of those examples of how we improved the methodology using these recommendations, and then a little bit more. So the characteristics of these 13 different models, what they include as the combined sewer area, storm drainage area, direct drainage area, how many smaller pockets of land that are driving the runoff generation process and then getting into the sewers and so on. If we want to discuss some of these details later on, we can. So the calibration process itself is to start with what we call as a site scale calibration, to do upland calibration, to understand the translation of rainfall into runoff, understanding the initial losses that happen in the system. There were several meters that were placed during our 2009-2010 Plan NYC studies, and also several other parallel studies. And once we performed this hydrology calibration, we moved on to what we call as area-wide calibration, which is looking at interceptor system or regulator structures and so on. These are heavily influenced by the hydraulics of the system. And then we also supplement with system-wide data that we have, the treatment plant inflow data that I mentioned. We also have over 110 regulators with the SCADA system that's tracking the water depths, and then also CSO facility data. Once we built the Flushing Creek tank, Paragut Basin and so on, we've been collecting data as to how much is coming in, how much is captured by these facilities and so on. We use all of this variety of data sets to support the modeling process. One of the key improvement that I mentioned was the imperviousness. Columbia University helped us with this characterization process. So instead of using this building footprint and then approximating the increased imperviousness, they used the spectral mixing methodology or analysis that identifies the bare soil or vegetated cover, and it's able to identify them using the different spectra. And then once we identify them, then the complementary pieces are the impervious areas. So what you see here, these are all the impervious areas within the system. These are identified as the pervious area. And what you see here as impervious is all what we call as total imperviousness. It doesn't mean that every drop that is generated from these is reaching the sewer system. There is a lot of things that happen, potholes holding the water, there's seepage happening, there's water stagnating in the low-lying areas. It's not reaching the sewer system. So we defined a metric called effective imperviousness area, also called as the directly connected impervious area. So you know how much it rained on the land, and you, from the monitoring program, you know how much got into the sewer system. You find the ratio, right? And if you're able to do that for a number of rain events and develop a set of parameters, that becomes your hydrology parameters. Then you can use that confidently for future storm events or other storm events and say this is the runoff volume that is generated from that specific rainfall. So these upland monitoring, there were 20 locations in total distributed in all the 5 boroughs. There are 2 sets of, 2 different periods that we monitored for. So the phase 1 is in red and the 2 in yellow. We selected the land uses for each one of these to be diverse. Some areas with high pervious area, some with medium, and then there was some on the high end. Some representing a lot of single-family residential as compared to some others with good industrial, commercial type of land uses. So the overall goal was to make sure that we get the best correlation in all the 20 locations. So we measured in 20 locations and we learned a lot of lessons and applied them for all the non-monitored and unmonitored areas of the city. So zooming in to one of the areas in Newtown Creek. So this is the site number, sites 7 and 8. So 1 meter was placed here because it was largely getting response from cemetery area with the high level of pervious cover and with a little bit of impervious covering here. And then the next site, 8, the downstream, that not only included this but a lot of localized land uses, denser area. So we defined the surfaces like there's an impervious cover that includes the public right-of-way, roofs, parking lots, driveways, etc. And then the pervious area, we define them with 2 distinct categories. One is this large pervious areas like cemeteries, parks, etc. that are not subject to a lot of compaction. Fewer people are going there as compared to residential lawns or commercial lawns and so on that are subjected to a lot more compaction. So we define them as open, that includes parks and cemeteries, and then a non-open, the other type of pervious areas. The radar rainfall data, instead of using the 3 airport data and also the Central Park location data, for this entire huge New York City metropolitan area, we obtained 1 kilometer by 1 kilometer rainfall data from a vendor. They supplemented not only the standard gauges maintained by the federal government, but also they use the Weather Underground, New York City's own gauges in several locations. They use all of them to calibrate the radar rainfall information. And we use them for both phase 1 and phase 2 site scale calibration that I mentioned. And how good is the model? We used what is called as a weight of evidence approach because there are qualitative and quantitative processes involved. So it involves both of them in terms of the metrics, but then one key recommendation in that approach is to use different scales. You do the calibration at the site scale or upland location. You also do it at the meters that are far downstream, but you also use the treatment plant. So you're using different spatial scales to gradually improve confidence on the model construction. So some of the metrics that included were, we used scatter plots of monitored and model data, volumes and so on. I'll show a couple of examples. And then we do the time series of flow comparisons, temporally how much runoff came into the system and what that resulted in terms of the overflow volumes and so on. So this is an example of the volume comparison. So each one of these dots represent one rain event. Okay, so the blue diamond represents the calibration event, and the red circle validation. On the x-axis is the volume, the total observed volume in the monitoring program. And what you see on the y-axis is the modeled volume for a specific event. So if they are exactly matching, you will be on this 45-degree line on the blue line. Okay. And then we developed some thresholds defined by international standards from UK. So if you are within this bound for most of the events, you call this calibration reasonably good. So volume is one of the metrics. And similarly, we did the peak flow that is getting to these metering locations. And same thing, observed versus modeled on the y-axis. Model depth of flow in the sewer, where we also track that as a metric. So again, these are the thresholds, and if your model depths are within this bound, it's generally pretty good. An example of the time series where you have flow, this is the dry weather period, and then flow starts coming in, and then during the peak event, peak flow was here, and then it starts subsiding. So the dotted values are the observed, and then the line is the model. So again, we see a general, decent calibration, we use as a metric for assessing the adequacy. So we'll now take a short break in terms of answering any questions that you may have on the watershed modeling. There's a lot of material that we went through in 15-20 minutes time. Before getting to another heavy topic of the water quality modeling, if you have any quick questions, we will recognize you will have another opportunity to, at the end of this process for our Q&A and discussions, but any immediate thing that you may want to ask now, please.
Yeah, when you were talking about the mathematical models, when you were talking about the actual measurement of water in the system, and if so, do you all look at the quality as well as the quantity of the water?
What we measure, in the flow metering programs that I have reviewed quickly so far, we typically measure the flows. So we keep the meters for, let's say, 3 months or 4 months period, continuously recording what the flow volume is, peak flow rate is, or depth of flow is, and so on. So during the dry periods, you get a clear idea of what the sanitary flow that is coming, up to that point. And then during wet period, you get the runoff response, so you start adding them up. And then with the multiple metering programs that we have, we are able to track the volumes as to how much is going towards the plant versus how much is overflowing. But in order to support the estimation of pollutant loads to waterways, we conduct targeted water quality sampling programs. So it's typically done for the conventional as well as some of the toxic parameters and so on. And the widespread, the professional methodology that I have seen nationwide is that they develop what is called as event mean concentration. For example, stormwater, has certain total suspended solids or metals that are coming from that stormwater source. You measure that for 3 events or 5 events and so on. Each time you do, you monitor the entire event and then see what the variation in concentrations are, and you take a representative concentration value from that monitoring program. So again, that is the calibration process. Once you have those numbers, then you use the model to generate the flow volumes and then associate the concentration for stormwater as well as the sanitary flow to get what goes out as a combined sewer overflow pollutant flow. Does that answer your question?
Because I just want to know, the water table in certain areas may be a significant measurement. Do you include the water table measurements?
It becomes a key factor during dry periods. When you have infiltration, groundwater infiltration coming into the sewer system, we do see that. Especially in the CSO control facilities, which are really at the end of a large drainage area, like Flushing Creek tank that's almost has a tributary area of 6,000 acres. So it gets like in the range of 6 or 7, 8 million gallons per day as the groundwater infiltration. But the way we model is that it is already part of our sanitary flow contribution, because except for cases like this retention facilities, again they get pumped and sent back to the treatment plant, so they become part of the sanitary flow estimates.
Yeah. Is there a margin of error for the volume projections for each water body in the InfoWorks model, like plus or minus 10% or something like that?
I didn't go into those type of numbers in the error bands that I showed in the calibration. So for volume, we use plus 20 to minus 10%. The reason why you see the plus to be a larger value is that we would err on the conservatively higher end of flows. So we allow more the model to calibrate a little on the higher side, but the tolerance on the lower end is lesser, right? So when after your calibration process, then typically what we do is conduct sensitivity analysis with different rainfall conditions and so on to get more confidence. Even though we may not have the site scale data, right, we still use the plant inflow data and then the SCADA system data. We run them on an annual basis. In fact, we have as part of our other permit requirement, we have to report the overflow volumes from all the combined sewer drainage areas to the state. So we have been using them, and generally, if you look at the balance at the treatment plant, it's very good. It's I would say within 10% is common, from our sensitivity analysis.
I assume that it's the margin the margin of error has gotten more accurate over the time. You guys have been developing this model for quite some time. So do you know what it was at the beginning versus what it is now?
Yeah, I couldn't quantify that, but one of the recommendations, if you remember from the peer review process, was to use more rigorous criteria, because in earlier methodologies also we had done the time series comparisons and so on, but we didn't really have those scatter plots to say, are these within plus or minus 15%. We generally looked at them in a qualitative sense, but with this peer review process, we tremendously enhanced that calibration process, and then thereby increasing the confidence on the models. Yes?
A simple question. The Columbia University drawing showed green, and that green represented air, soil, and plants, right?
Yes.
But, and they're assumed to be pervious.
Yes.
Or permeable. But I guess how do you address, and you talked about this a little bit, the cemeteries and the parks, but how do you address the degree of permeability across the city within this model? Because you have some areas that are very sandy, you have some areas where the soil is really compacted.
Mm-hmm.
It's a very different kind of condition.
Right.
So is that something that's factored into your model?
I want to say yes to a degree, but at the end of the presentation we have the next steps, which is one of the things. Current calibration process focused on the entire city. You saw that 20 locations distributed in the 5 boroughs and so on. One of the key things that really differentiated in the way that we were getting responses was the density of single-family residential versus commercial and so on. So the pervious area within one area, for example, with a large number of single-family, even the impervious factor, even though they are high, the runoff response that we got was much less, and then so we had to apply some degree of variation based on the land uses already. But when we collect additional data sets, we are planning to do that as part of the long-term control planning. We already have identified some data gaps in some drainage areas. I easily anticipate, revisiting the model at that local scale and making some adjustments as we go into the LTCP process.
Are the flow meters, the upland areas, are they capturing any data from where you've done green infrastructure interventions or other agencies? And can you already show some response of the data to the creation of green infrastructure interventions?
Not through this monitoring program, but we have neighborhood scale projects ongoing in 3 different areas, in 26 Ward, Newtown Creek, and then the Hutchinson River watershed. And these are exactly supposed to measure what you're referring to. So we have been monitoring before construction. That way you understand the baseline. But as we are building 10, 12, 20, 30 bioswales, we want to see the progress in progression in terms of the reduced flow and also the water quality in the sewers. Those measurements are done within the sewers at a much smaller geographical scale than even what I mentioned here.
Probably it's too large a scale to see those changes in these much larger areas.
Yeah, and it's a little early to do that kind of monitoring on a system-wide basis, mainly because we have probably less than 100 right-of-way bioswales on the ground now, but there's a lot more, thousands to be built in the next few years. So that's where we'll start to see bigger differences even in that scale.
But it seems like you already have the data for this. You're getting creative differentiation from your prediction as you start to get higher volume flows. And if the systems behave like all other flow systems, you would expect that your coefficients of discharge will change both for your pervious and impervious zones as you start to get higher flows. So you should be able to resolve your model potentially from, if you have the large storms characterized, storms characterized according to size, you should be able to get better resolution just simply taking the scale of impact and the volume flux which is already in your model, already plugged in, right?
Right. But the thing is, though, as the rain volume increases, your fit is going to be a lot better also, because the thing is, at that point, the pervious area also is acting like impervious area after filling all the.
Right. So you should be able to use an allometric correction, so to speak, on your different sub-watersheds and resolve your model just from that data, and that data is already in you're already.
Oh, you mean for the green infrastructure?
For everything, but for green infrastructure is an issue because of the scale of it, right? So far it's small, but as it gets larger. Right. But your surrogate for green infrastructure is going to be Prospect Park, your cemeteries, your basically zones that are already green. Right. You already have that data. Right. You have the output data and swarms of different scales. You should be able to take that and say that since it's going to be, you're assuming a linear output, and it's not that. You know that from your pervious and impervious areas. Mm-hmm. If you can basically resolve your export coefficient from the scale data you already have, right, you should be able to resolve the difference between your prediction and your model data and your actually gathered data you gathered right now.
Yeah. Well, the thing is, I skipped a slide on the detailed model parameterization. For the 3 distinct surfaces that we talked about, and how those are varied based on the density of single-family residential, as well as the presence of larger pervious areas and so on. But I can share with you, Paul, on the details. Yes, it is in the model calibration report that's being reviewed by DEC at this time. Once we have that in final form, or even before that, I can share with you.
How do you account for the impact of tree canopy on top of the impervious area and then rooms that have been disconnected from the sewer system? A lot of houses in historic districts, for example, discharge their roof bars straight to their gardens. How is that integrated into the purpose?
one of the key thing related to tree canopies that we are essentially, if it is above impervious area, we are treating that as an impervious area. So we are creating extra runoff than what can be in the real world, which is kind of on the conservative side. But at the scale that you're looking at, the land parcels that are contributing runoff to the 48 inches and larger sewer system is generally like 50 acres or 60 acres, 80 acres, and so on. So at that scale, you start losing that brief, delays that you get, especially once you start getting larger storms and so on. You don't even see that as you get to that 80 acre scale. But where it gets to be important is, if you're looking at, 5 acres area with 30 or 50 right-of-way bioswale installation with a lot of trees, with a large tree canopy, you will see that difference. We can reflect that in the model as we go to that level of resolution. Yeah.
I was surprised when I read a report about the amount of capacity that was regained when the silt was removed from the system last year, I guess it was, the report. And I'm wondering if any of these models measure silt and floatables during storm periods.
Maybe I'll cover the first part. We have a consultant here who has been helping us with some of the floatables characterization. Sediment levels, you can model them within the sewer system as a fixed, silt, not the dynamic one that kind of moves along as the flow goes by. You can represent the depth of pipe occupied by the silt, and as a result, any reduction in hydraulic capacities of sewer elements. But it gets to be, for looking at your specific comment on the system capacity, the interceptor sewers certainly have benefited from the cleaning process. Especially some of the areas you have these concrete blocks, thrown. It's definitely not PEPs, that dumped concrete blocks, but there are a lot of stuff that is in the interceptor sewers. Once we removed them, we certainly saw significant capacity increases in the interceptor system. Tom, you want to comment anything on the floatables modeling process?
We don't see floatables as an issue of obstructing the flow in the sewer system. I think more where you would see floatables obstructing flows on the streets, where you have floatables that end up on the catch basin grates, and then the flow can't get down to the catch basin, so it skips and goes to the next catch basin.
But we have developed an empirical methodology. Tom worked on characterizing the different type of litters that we get typically from land uses, and then using their floating characteristics. Because as part of one of this permit requirement, we need to report on what our floatable controls measures do. Either it is a net that's around the outfall that is capturing all of those, what kind of retention or removal rate that we do. We have been doing some empirical modeling of that, but in terms of the blockage, they generally tend to clog that catch basin, but once they get into the system, they have enough velocity to get carried to the treatment plant.
Are you seeing any consistent correlations with intensity and duration of storm for the predictions that are high versus the predictions that are low? Are you grouping all the ones that are a little high and then all the ones that are a little low and looking for correlations?
Are you thinking in terms of the intensity and volume characteristics?
Yeah, I'm wondering if there's anything consistent for
the storms that were captured, during the calibration process, that's one of the key things that you need to recognize. You just don't put the meters in, once you get the two storms, you take the meters out, but you start looking at the characteristics of individual storms. Do we have smaller storms that represent, more like, the initial losses that happen in the system, like the infiltration filling up the potholes and so on before the runoff gets generated, right? For the first half an inch, or a third of an inch, you may not get any runoff response from a certain area. And then once you start going above that, you start to see a linear relationship between the rainfall and runoff, because at that point, all the losses are met, everything is getting into the sewer system. So we make sure that there are enough storm events of different characteristics, some with shorter duration, peaking intensity, versus maybe 6 hours, 8 hours, 12 hours type of rain events that can stress the system for a longer period. So we make sure that we have enough number of events to sufficiently calibrate the model. And then when you also, when we validate the model, with the different type of storms, and see that the performance at the treatment plant is pretty good, and then some of the other meters are pretty good, then that's how you start building enough confidence on the model so you can use it for any type of rain events from that point.
So you're not seeing any consistent correlations when you look at the hydrographs?
Yeah, I'm sorry. I was about to go on with the presentation, but Paul had a similar question, and it's pretty much a scatter plot. I don't see any trends that go away from the linear for the biggest storms where it produces more volume. We can take a look again, but it tends to be pretty linear and seems to jump on either side of that line. And again, we can answer these questions after the presentation. I just want to give Tom some time, and I'm sure we'll be back too. Thanks.